Hi everybody, today Madeline and I are going to discuss the paper by Luetkemeyer on femoral entheseal shape and attachment angle as potential risk factors for ACL injury. Before we begin, I want to reiterate a few key points in the Mallet paper discussed by the group prior. This paper used experimental models to determine the mechanical response of bundles within the ACL. They concluded that the AM and PL bundle do not share the same properties, noting the AM bundle was stiffer. Mallet recommends independent characterization of bundles in future studies. This paper focuses on a part of the ACL called the femoral enthesis, which is circled in red. This is the location within the ACL of most non-contact tears. Previous studies have characterized this structure in 6 different ways according to their tide mark profiles, or concavity, as well as how the ligament is attached, with a focus on the angle at which the ACL connects with the femur. This paper used these characterizations to analyze the distribution of strain in both 2D and 3D models. On the right-hand side is the different categories determined by Bolu, just as a note that these figures are based on the figures within the actual paper. So this figure shows the 6 different profiles based on the shape of their tide mark. This paper often focuses on the profile shapes that are either convex, which are all shown on the left side, or concave, which are all shown on the right side. It is also important to note that this paper created models based off the average male and female insertion angles. The ACLs for each model were at a 15-degree flexion. Before I discuss the methods and results of the paper, I want to emphasize the goals. The first goal was to use the tide mark profiles and attachment angles previously found to develop models of the ACL femoral attachment. The second was to analyze the differences in strain among these profiles to determine which characteristics are more prone to injury. This paper has 3 main methods. First, a 2D analytical model, followed by a 3D FE model, ending with a macroscopic stress-stretch simulation. After each method is explained, the results will be followed before proceeding to the next method. Figure 2 represents the relationships used within the 2D model. The width was fixed to the curve denoted A of x. This line shown in red is characterized by the 6 tide mark profiles, which you'll see shortly. The slope was made so that the insertion angle was either at 13 or 7 degrees. Finally, a uniform displacement was applied to the length. The researchers used these parameters in equation 1 to determine the displacement field. The displacement field was conceived under assumptions of homogeneity and no Poisson effect. On the left side of the slide, you can see the equations that were used to create the A of x parameter. These equations describe the different tide mark profiles as well as the linear line. You should note that equation 2 through 4, or the top 3 equations, describe either the concave or convex profile for each polynomial in figure 1, hence the A through F subscript. This differentiation is made on whether you add the nonlinear terms, which will make it concave, or subtract them to make them convex. On the right side is the familiar equations used to find the Lagrange strain tensor. To find the strain tensor, the deformation gradient was determined based on the displacement field from the previous slide. The Lagrange strain tensor, denoted E, was used to solve for the equivalent strain, denoted EEQ. These are the results of the 2D analytical model. Due to the size of the images, they are also provided on separate slides so you can pause and have a closer look. These results show that the magnitude of maximum shear varies depending on the shape and attachment angle. In the middle row of figure 5, and also seen in 6A, there are higher strains in the concave profiles. The bottom row of figure 5 as well as 6B show the equivalent strain results for each profile. Again, the concave profiles have increased equivalent strain. Figure 6 also shows that the angle at which the ACL is inserted greatly affects the amount of strain seen within the system. Here's a closer look at figure 5. Here's a closer look at figure 6. The next method discussed in this paper is the formulation of the FE model. Figure 3 shows the convex, concave, and linear shape profiles for the models as well as the boundary conditions. The models all had 10 millimeter diameters and net attachment angles of 13 degrees. The boundary conditions on this model are constrained entheses and axial displacement prescribed at the top center and free radial displacements. The researchers used an axial stretch of 1.1 because it is far from small strain, but still within the physiological range of the ligament. This analysis utilized three constitutive models. The first model described the ligament as isotropic, the second described the model as transversely isotropic, and the last was also transversely isotropic. However, it was freely jointed. These constitutive models are noted as neo-Hookean, HGO, and FJC. The mechanical properties of the ligament were assumed to be the average of uniaxial responses from each of the bundles. From the results of the mallet paper, we know that each bundle has unique properties. The transverse behavior of the ligament was modeled from the data of Quap and Weiss as well as Henninger. Figure 4 depicts the best fits along and normal to the preferred material direction. There is a large variation in the transverse experimental data compared to the constitutive models, which is seen in B and C. The best fit for data along the preferred material direction was aligned fairly well. Figure 7 shows the maximum tensile and equivalent strains for each ACL enthesis geometry and material model. If you look at B and D, you can see that the entheses that were concave showed the highest equivalent strain, and those that were convex showed the lowest. However, depending on the model and source of data, the magnitudes were varied. The FJC model showed large differences in maximum equivalent strain between the Quap and Weiss data and the Henninger data. Finally, if you look at A and B, you can see that there is no consistent trend in the geometry effect on tensile strain. The last method discussed was the macroscopic stress-stretch simulation. This simulation assumed uniaxial tension. Note that this assumption is contrary to the findings in the mallet paper, where they said that the homogeneous uniaxial tension is not achieved when shear and transverse strains are large. However, this paper indicates that there is an unknown extent to which the results are affected by this assumption. The macroscopic stress-stretch relationships were compared to the experimental data to understand what constitutive models fit best. The results of the simulation are shown in Figure 8. Please note that the Quap and Weiss data are shown in A and B, and the Henninger data is shown in C and D. The response in the FJC models in B and D showed a stiffer response than the HGO models, which are shown in A and C. It is also important to notice that the data from Quap and Weiss produced a stiffer response than the data in Henninger. In A and C, as well as D, the convex attachments yielded the stiffest stress-stretch relationship. For B, the concave attachment yielded the stiffest response.
The results of the models provides insight into several aspects of ACL injury, including possibly why ACL failures often occur at the femoral enthesis and why females seem to be more at risk for ACL injuries than males. Some other key points touched on in the discussion of this paper was possible loading effects on enthesis shape, future directions and consideration for additional research, and the limitations of this study. The results of this study show that when there is an acute attachment angle of the ACL at the femoral enthesis, there is usually a concentration of shear strain, especially at the most distal point of attachment. The results also showed that a concave tide mark profile exacerbates strain concentrations, whereas convex profiles mitigate strain concentrations. Although both the attachment angle and the tide mark profiles were shown to have an effect on strain concentrations, the authors concluded that the attachment angle is more influential in creating concentrations of shear and equivalent strains. However, the profile shape is related to the attachment angle in that concave profiles generally minimizes the attachment angle and convex profiles generally maximizes the attachment angle. Concentrations of strain due to an acute attachment angle also possibly explains the increase in ACL injury risk for smaller femoral notch widths, since those with small notch widths generally also have more acute attachment angles. The strain concentrations correlated with more acute attachment angles is also a possible reason why females are more susceptible to ACL injuries than males. According to Beaulieu et al., the mean femoral attachment angles of females was found to be nearly half that of males. In addition, Beaulieu et al. Also found that 81% of males have convex profiles, whereas only 57% of females have convex profiles. Considering that females are more likely to also have smaller notch widths, and in addition to the concave profile, thus having a smaller attachment angle overall, they are also more likely to be susceptible to higher strain concentrations and thus are more at risk for ACL injuries. Though in this study, the ACL was modeled as a single bundle ligament, the ACL actually has a posterolateral or PL bundle and an anteromedial or AM bundle. Previous studies have shown that the PL bundle is more susceptible to damage than the AM bundle. This is possibly due to the fact that according to Beaulieu et al., all concave profiles were found more posteriorly in the attachment site, and all but one convex profiles were found more anteriorly in the attachment site. Thus, the PL bundle is more susceptible to higher strain concentrations due to its concave attachment sites. Additionally, the shape of an enthesis might be subject to remodeling and adjustments according to external loading conditions. Malala et al. Found that enthesis shapes are significantly different in dominant arms versus non-dominant arms. Beaulieu et al. Found that 70% of all enthesis profiles were studied were convex, suggesting that convexity is naturally favored over concavity. None of the current conclusions are supported by concrete study and therefore should be considered for future research. One of the questions we will be submitting for discussion is, why is the possibility of a loading response causing shape change of the enthesis relevant to this study? Why is it significant in understanding ACL injuries? As Abby mentioned earlier, the study in this paper based its macroscopic stress-stretch analysis on two separate transverse datasets. Even when the same constitutive form and axial response dataset was used, the two model fits from the two different datasets provided disparate results. Furthermore, different constitutive models also produced dissimilar results. The mismatch of computational results to experimental results indicates that the transverse and or shear response of the ligaments might be important to consider for future studies. Also, currently there is not enough experimental data in multiple deformation states to be able to concurrently tell which material model is accurate, or even to ensure that all model parameters have been identified. Despite the variation in results from the different models, every model still showed that concave enthesial shape increased max equivalent strain, also increasing chance of injury. Previous studies have always assumed that the mechanical response of transverse fibers is negligible, but according to the results of this study, the transverse mechanical behavior does indeed play a role and should be also considered in future studies. For both the different constitutive models fit to the same data sets, as well as the same constitutive model fit with different transverse data, the macroscopic stress values varied widely for a given macroscopic stretch. This misalignment of the global stress-stretch curves and constitutive model fit, as seen as Figure 8, implies that the boundary effects are preventing the models from achieving a state of uniaxial tension, which was originally assumed for the material model fitting. Current constitutive models describe structural and material stiffness. These properties should be decoupled for an accurate FE model, especially in highly transverse isotropic materials. The geometry and boundary conditions of the sample has an effect on the macroscopic mechanical behavior and should be accounted for in future studies. The authors needed to make several assumptions and was subject to limitations over the course of this study. Several of these include the use of von Mises criterion for anisotropic materials, simplifying the constitutive model assumptions, the use of a single bundle model instead of a double bundle model, using data collected at a 15-degree angle, although this is a common angle for the injuries to occur, so it was a logical choice of angle, idealizing the cross-section as a circle, not including bending, torsion, or other non-axial displacement in the applied deformation, and assuming homogeneous uniaxial tension. In conclusion, the primary goals of this study were to model the femoral attachment of the ACL to determine if the tide mark profile and attachment angles causes the ACL to be more prone to injury. The study results showed that a more acute attachment angle and concavity of the attachment site increased the equivalent strain, causing a higher chance of injury. A secondary goal of the study is to use the formulated models to test the validity of the traditional constitutive modeling assumptions. The study found that the common assumption of homogeneous uniaxial tension is not valid, and that transverse mechanical response of the constitutive model has a significant impact on the strain and macroscopic response and cannot be neglected in future models. Thank you for watching our presentation. We will be posting relevant discussion questions in the forums to help inspire discussion. If you have any questions for us about the presentation or the paper, please post them for discussion and we will get back to you. Thank you and have a great day.